continuous term quantum works for the max cut hot. It's very fantastic title. So please start your talk.
Thank you very much. So thank you very much for coming to listen to me today. And I will be telling you about why continuous time quantum walks and max cut are hot. And this is work I've done here at UCL with Dan Brown and Paul Warburton. And the details can be found in this recent publication in Quantum. So, okay, so brief outline of my talk. I'm just going to motivate quantum walks and introduce the steps involved in them. To gain some intuition, I'm then going to look at the very short time limit. From here, I'm going to discuss what it means to optimize a quantum walk. And then I'm going to discuss thermalisation. And using thermalisation, I'm going to build a model of these quantum walks. With this model, I'm going to try and optimize them and then give a brief extension to a multi-stage quantum walk and then provide a rough summary of the work so far. So why should we care about continuous time quantum walks? This is by no means an exhaustive list, but a couple of their successes. Well, they've been shown to achieve the same scaling as Grover's algorithm for unstructured search. And in a comprehensive numeric study, they were shown to achieve a better than Grover's scaling on spin classes. So I think continuous time quantum walks deserve our attention. And this is what we're going to focus on today. So what makes a continuous time quantum walk, especially for max cut? Well, you start with some graph on which your max cut problem is defined. For the purpose of this talk, all our numerics will relate to binomial graphs where each edge is selected with probability 2/3, but this could be in principle any graph you're interested in. So from this graph, you construct your drive and problem Hamiltonian, just as you would in quantum annealing. For the drive here, we've taken the transverse field driver, which you can think of as being a quantum walk on the Boolean hypercube. And for the problem Hamiltonian, I've taken the standard Ising formulation of max cut. So we take these two Hamiltonians and we add them together with some parameter gamma to get the quantum walk Hamiltonian. We take this time-independent Hamiltonian and we evolve our system from the ground state of the drive Hamiltonian for some time t. After then, we sample and hope we find good quality solutions to our max cut problem. So this Hamiltonian is the quantum walk Hamiltonian, and it appears, I think, deceptively simple. And part of this talk is sort of building up the language we need to reason about its behavior, where exact diagonalization is prohibitively difficult. And to get some intuition to begin with, let's focus at the easiest limit, which is the short time limit. And in order to discuss the short time limit, we should probably start setting some time scale. So to do this, we're going to focus on the torsion. So this is a geometric quantity, and it measures how much a system deviates from a two-dimensional subspace. Now, when you calculate the torsion, it only depends on expectation values of powers of the Hamiltonian, which means it's going to be constant for our entire evolution as we have a time-independent Hamiltonian. And we can calculate it analytically. It's pretty straightforward. And we see that it depends on the number of edges, triangles, and squares in the underlying max cut graph. And even from here, we can start gaining some insight. So we can see that the number of triangles, which we might associate with frustration in our max cut problem, reduces how quickly the quantum walk searches the Hilbert space. So now using torsion, we can set a timescale. So for t less than 1/4 of the torsion, our quantum walk can be approximated by a two-level system. And within this time window between 0 and t, it's relatively straightforward to calculate expectations of observables, such as the problem Hamiltonian shown here. And we could have a look about how this compares to the Schrödinger evolution. So here I have two continuous time quantum walks for max cut on the same binomial graph for 12 qubits. On the left, I have gamma equals 1, and on the right, gamma equals 0.05. The blue line shows the Schrödinger evolution of HP, and the pink line shows the short time prediction. The dashed purple lines show 1/4 root of the torsion, where we expect this short time prediction to start breaking down. For gamma equals 1, we see this is indeed the case. But for smaller gamma, even beyond this limit, the Schrödinger evolution is, let's say, qualitatively, if not quantitatively similar to the short time prediction. So we're already building up some intuition about what we expect expectation values of HP to depend on. And we also have some idea of a timescale now associated with continuous time quantum walks. So let's look at the second limit, which is the long time limit. And we're going to talk about optimizing continuous time quantum walks. So what do I mean by this? Well, in our quantum walk, we have this 3-parameter gamma. What we'd like to do is optimize this gamma in some way. And to do that, we need to choose some metric by which to judge which gamma is better. So we could look at, say, the ground state probability. In general, this is going to be difficult to know for problems of interest. Or we could look at, say, the expectation value problem Hamiltonian, which we would like to be as small as possible. And for the purpose of this talk, we're going to focus on this. So we want to find the gamma that minimizes the expectation value of HP. The question is, at which time? So here I have a 12-qubit binomial graph again. And the blue line shows the Schrödinger evolution of HP. The pink line shows the ground state energy of the problem Hamiltonian. Now, if the blue line representing the Schrödinger evolution had reached the pink line, it would have found the ground state exactly. But we see this isn't the case. Instead, the expectation value of HP is oscillating around some steady state value, shown here by the dashed purple line, which is the time average value of HP. So instead of optimizing for any given time, what we're going to aim to do is try and optimize for this time average value. This brings me on to my second point on this bit, which is thermalisation. So it's well known that closed systems can thermalize, and this is sometimes referred to as the eigenstate thermalization hypothesis. For the purpose of this talk, we're going to say a system that is thermalized is locally indistinguishable from a Gibbs state. So if we have a Gibbs state, we need to fix the temperature somehow. And to do that, we use the fact that energy is conserved in a closed system. So all we need to do is solve this equation here to find the inverse temperature beta, where n is the number of qubits. And we can at least do this numerically for small problem sizes. And here we have a 12-qubit instance. The blue line shows the Schrödinger evolution again, and the dashed purple line shows the prediction from the Gibbs state, where the temperature is fixed according to the energy. Importantly, this has no free parameters. But we'd like to go a bit further and discuss regimes where we can't do exact diagonalization. And to do that, we need to build a model. So to make progress, we're going to try and model the density of states. And to do that, we need two things: a probability density function and a method for fitting to this probability density function. I'm going to focus on the second of these to begin with. So what we can do is fit our probability density function using moments of our density of states. So it's relatively straightforward to calculate moments on the density of states, which is given by this equation here, where k corresponds to the kth moment, and this is relatively straightforward to calculate for low moments. So using this, we can start with a guess of our probability density function, which we should take as a Gaussian. We can calculate the mean and the variance analytically using the moments shown prior. And we see that it depends on the number of nodes, the number of edges, and the underlying max cap graph. And we can compare this to a numerical experiment. The blue shows the density of states for a 12-qubit binomial instance, and the dashed black line shows the Gaussian with parameters shown on the left. Now, the Gaussian is sort of capturing the right shape, but we can see that the density of states is skewed, which isn't being captured by this Gaussian. So let's calculate the skewness, which is associated with the third moment. And we can see that it depends on frustration in our problem Hamiltonian. And importantly, depends on the number of triangles. So now we've calculated the skewness. Let's try and use it. And to do that, we're going to use an exponentially modified Gaussian, shown here in red. And we can see we're doing much better, sort of capturing the skewness of this distribution, albeit imperfectly. So what is an exponentially modified Gaussian? It is simply a convolution of an exponential distribution with a Gaussian, and it's a probability density function with three free parameters, which we can fit quite easily with the first three moments of the density of states. Although its PDF might be slightly complex, since we're actually only interested in the partition function ultimately, given that it's convolution, it's pretty straightforward to work with. So just to summarize the model, I'm going to assume that the steady state behavior of my continuous time quantum walk is well modeled by a Gibbs state. And I'm going to assume that I can model the density of states well with either a Gaussian or an exponentially modified Gaussian. So now we can predict the temperature, where Z is the partition function associated to whichever model density of states we've chosen. And we can do this with both the Gaussian and the exponentially modified Gaussian. And again, n is the number of qubits, kappa 2 is the number of edges, and kappa 3 is the number of triangles in our max cap graph. So focusing on the Gaussian case for a moment, we can see that the inverse temperature is always less than 1, hence the temperature is always greater than 1, and continuous time quantum walks are hot. A similar thing holds true for the exponentially modified Gaussian. And if we wanted just to do a sanity check with numerics, so here I have for various problem sizes, 100 instances, and the inverse temperature calculated numerically without any approximation in density of states. And we can see that all the temperatures are less than 1. Okay, so we have the temperature, which is useful, but we'd like to go a bit further and try and find the expectation value of the problem Hamiltonian, which we can do with this equation here. And again, we can do this all analytically, and it's pretty straightforward. And again, we see it depends on the number of nodes, edges, and triangles in our max-cut problem. So what we would like to do is, instead of optimizing the true value of HP, we're going to optimize these values of HP to find the optimal gamma, which we would then run on our quantum device. But let's see how it compares numerically. So again, I have a 12-qubit instance. The blue line shows a direct numerical calculation of the time average value of HP as we change gamma. The dash purple shows the prediction from a Gaussian density of states, and the dash pink line shows the prediction from an exponentially modified Gaussian. As we can see, both of these distributions are capturing the shape of HP, with the exponentially modified Gaussian doing a better job. What we're primarily interested in is how well do they predict the optimal gamma? That is the gamma that minimizes the expectation value of HP. And we can see they're both doing quite well. So if we wanted to look at maybe some more numerics, we could look at how much the time average value of HP deviates from the gamma you would choose from looking at an exponentially modified Gaussian, and the gamma you would choose if you had access to HP, the true value of HP. And we could plot this for 100 instances for small problem sizes between 10 and 13. And as you can see, we're doing pretty well with being on average within a cut of the optimal value of HP. So here we've shown that we can optimize our continuous time quantum walks in a pretty straightforward manner by assuming thermalization and a model for the density of states. But we might ask if there are any possible extensions to this. And to do that, I'm just going to introduce very briefly a multi-stage quantum walk. So you can think of this as being sort of inspired by quantum annealing, where instead of having time-independent gamma, we have some gamma that increases in some stepwise fashion in a monotonic way. And we could look at a numerical example of this. So here we have a 5-stage quantum walk, where gamma starts at 0.5 and increases by 0.5 each stage. The blue shows the Schrodinger evolution, and we can see at each stage, it is approaching some sort of steady state value. And again, we can look at, does this thermalize? So the dash purple, or the solid purple, shows the numeric prediction from a Gibbs state. And we can see that it does pretty well. And that each stage, the system is thermalizing, which means it's not going to be particularly sensitive as to when we perform the next quench, assuming it's already reached thermalization. We could look at a prediction again from an exponentially modified Gaussian, assuming thermalization at each stage, and we see we're pretty close. If we wanted to build up some more numerics, we could do so. So this plot shows the difference between, so this plot shows the result from a 5-stage quantum walk with the same schedule as before, where gamma is increasing from 0.5 by 0.5 each time. The y-axis shows the difference between the thermal prediction of HP at the end and the true value of HP at the end. And we can see for the exponentially modified Gaussian, it's making a roughly unbiased estimate, but suffers from the accumulation of errors due to fluctuations in HP at each stage. While the numeric, if we just numerically fit a Gibbs state solely using the energy, we see we're making a pretty good prediction of HP. So even at this 5-stage limit, we're still very thermal. To provide just a brief summary, we've got a very simple model that allows us to make predictions about quantum walks. And these predictions depend on underlying properties of the max-cut graph, namely the number of edges, triangles in our problem. And if you're interested in finding out more, you can find more at this publication. With that, thank you very much.
Thank you very much for very interesting talk. So any question or comment from audiences?
I might have some
Yes,
questions.
please.
So,
Yes.
Arthur, very nice talk. Thank you very much.
My pleasure. Thank you.
Bobby. So first, I just want to make sure. So you start from the plus state at the beginning of our quantum walk. Do we have like some theoretical reasons to start from the state, as it's not necessarily the ground state of the Hamiltonian? Or...
Yeah, sure. So the sort of argument goes that since you're in the ground state of this drive Hamiltonian,
Yeah.
it can only go up in energy. So the energy of the problem Hamiltonian can only go down, at least to begin with. So with that, you have a proof that you can always do better than random guessing. But I think that's as much as you can say.
Okay. All right. And then, so you introduce the torsion. So I'm not familiar with this notion. So when you manage to have like this analytical equation of the torsion for the graph in max-cut, where you have the number of edges, the number of triangles and square, is it true only for short time or?
So the torsion is true always.
Okay.
So that's conserved throughout the evolution, and it's just a measure of how much your state deviates from a two-dimensional subspace or from a block sphere, if you like. And
Okay.
it's really easy to do at the beginning because you know your initial state, so you can just build up a two-dimensional space by just moving forward a little bit.
So it's when you do this reduction to a two-dimensional. Okay. All right. So I have a few more questions, but if other person have
Okay. Yes, please continue your question.
Yeah. Okay.
So you try. So if I understand, you try to get close to the Gibbs state of the quantum walk, or
so I suppose the argument is the system already resembles a Gibbs state. I don't have to do anything.
Yeah. Okay. Yes.
Yeah.
And yes, but when you do this, so when you try to when you do the model of your Hamiltonian, you're trying to have the best final expectation given the model you have of the Gibbs state you think you are reaching, right? And this depends on gamma.
Yeah.
And then you optimize gamma. Okay.
Yeah.
Okay. And have you observed some worst case scenario, like some worst structure of your graph for this problem, or?
Oh, what do you mean by worst case?
For example, when you have this box plot,
Yeah.
you have like some outliers.
Oh, I see.
You know which structure of your graph makes quantum walks triggers the most?
See. So there are a lot of okay. So there are two things I think that can cause. So sometimes they just don't look particularly like a Gibbs state, which means we're off when we're all trying to optimize them, but doesn't necessarily mean they're hard for quantum walks.
Okay.
And sometimes it's just a case of these are more difficult problems. I can't remember exactly the structure of these. It's been a while since I looked at them, but I can get back to
of course.
sure.
But yeah. So you don't know if there are like many triangles or no triangles at all, or? Nothing is that simple, I guess.
Oh, actually, I think my guess would be that triangles aren't a problem. We're keeping kind of triangles, but say if it had a lot of pentagons, or it had
Yeah.
no triangles and just pentagons, our model wouldn't capture that, right?
Okay.
And it would
Yes.
still be frustrated.
Okay. Well, thank you very much for answering my question.
Right, it's my pleasure.
Good. So any question, comment? I have a short question. So you consider the continuous time quantum walk
Mhm.
and for MaxCat
Yeah.
graph. And I'd like to know that is it possible to experimentally confirm your prediction, like using the quantum optic system or a cold atom or something? This is because that quantum walk was already experimentally realized in such quantum
Yeah.
optics system and some other physical system. So maybe it's quite interesting to experimentally confirm your prediction. Is it possible?
I agree with you. It would be cool to find out. So there are, I suppose, two things.
Mm-hmm.
One is, right, how do you, well, so one is just the experimental challenge, which is you quench quickly enough.
Mm-hmm.
So you need to have some sort of idea of the timescale of your system. But I think the bigger problem, more theoretical side, is this isn't going to be a closed quantum system anymore. So you're going to have some bath, which perhaps is got, if you like, a closer to continuity density of states. And whether this bath dominates, if you like, over its internal bath, I think is something I've not quite worked out.
Okay.
Still thinking about it.
I see. Okay, thank you. Okay, so any question, comment? Okay, if not, so let's thank us to the speaker again. So thank you very much. Very interesting talk.
Thank you very much.
Okay. Very good. Yes. Thank you very much. Okay. So so Paul, any other announcement from INQA? No?
No, I have no specific announcements other than to
Okay.
thank you for an excellent
Good.
presentation. Thank you. Thank you for sharing, Shira.
So okay. Yes. So do you have 5 or 6 minutes
Yes.
after?
Let's
Yes.
wait for the
So I'd
meeting.
like to discuss about yes.